Hey guys, and welcome to a new video in this algorithm and data structures tutorial. In this video, we're going to talk about priority queues and what priority queues can be used for. And then in the end of the video, we're going over some like code examples of the different kind of methods that we can call on priority queues and how we can like implement a priority queue by using heaps in C++. So first of all, we just need to like know what a priority queue is, and a priority queue is like when we need to like execute queues by different principles that the FIFO that we talked about in one of the previous videos about the just the standard queue where it was like the first in first out. So the first element that came into the queue was also the first element that came out of the queue. Where in priority queues we have the elements they're like assigned a priority in the queue, so they're not like removed with the highest, like with the first element that comes into the queue is not removed, but like the element with the highest priority or like lowest priority, it depends on what kind of queue you have implemented. So if you look down here at the bottom, we have an example here of a queue where we can like insert an element. So in this case here, we're removing the least element like with the lowest priority, and then we're inserting elements with the highest priority over here to the left. So like the rear here will point to like the largest element in our queue here, or like the element with the highest priority, and then we remove here the least the element with the least priority here at the end here. We can also have like a queue where we like deleted the element with the highest priority, and then like just inserted items where it fit into the queue, so they're like in priority order. So there are different kind of applications for priority queues where we can use it for CPU scheduling, where we have some tasks that comes into the CPU, and those tasks has like different priorities. Like for example, let's say like we're moving the mouse around on a monitor here, then we want it to be reacting fast, so it could have been assigned like a high priority, and then it comes into the queue with a high priority. So that task will be executed before like some other tasks that take like probably like open up programs or stuff like that, which like it doesn't really matter if it takes 1 or 2 seconds to like open up a program compared to if there was like lag on the mouse. So it can be used for like CPU scheduling, like, or other like applications where we have like urgent orders, that where we have elements that comes into the queue, or that like arrives at different times with different priorities, and then we need to like get the elements with the lowest or the highest priority, and depending on the application. So we also have some different kind of methods and operations that we can do in our priority queue, where we can like insert an element with some priority into the queue, and we can also like delete the minimum element or the max element. And it also like depends on what kind of queue you want to implement, if you want to like delete the elements with the highest priority or with the lowest priorities. So when we're talking about priority queues here, we're using binary trees. Like we implement a priority queue as a binary tree. It can also be implemented with linked list and other like data structures, but it is more often used as with binary trees, because like the time complexity, and when we're accessing and inserting elements, then it's a bit faster. So the binary heap is used for a priority queue, and we can implement it as a max heap or a min heap. Where in the max heap we will have like the root node up here at the top here, so it will be the max element in the max heap. And if we were implementing as a min heap, it will be the minimum element like with the lowest priority at the top root node here. So we're also going to talk about like trees in later videos, but this is just to like give you a short introduction to trees as well. We're going more in depth with it in later videos, because there's like a lot of different kind of topics and methods we could do with trees by searching and inserting and stuff like that in a really fast way. So we will cover that in another video, but we're using binary trees to implement the priority queue. So we just get a quick overview here. So first of all, we have the root node up here, the A node here, and then we have like some child node. So A and C here will be a child node to A, and then B will be a parent node to D and E, which also are child nodes to B. So we have like these kind of different levels from the root node here, so we can like divide our binary tree in two here with different kind of levels. And then we have the depth here of the tree, and it is like in what depth we are in the tree. Like for example, B here we're at depth 1 because we have like an edge here that connects these two nodes, and then the depth of this element here will be 1, and down here will be 2. So we also have like the height of the tree, which is like the longest path to the lead node. So the lead node is the last node in the tree, which we are going to like cover more in later videos as well, where it's more convenient to talk about. So like a binary tree is also like a recursive data structure, and there's different kind of concepts in the tree as just talked about. Like we have the some nodes around here in the tree. We have the edges connecting the nodes. We have the root over here, child, parents, and leaves, and then the depth of the height of the tree. And then our tree can also be like complete, perfect, or a balanced binary tree, which we're also going to cover in later videos. But for implementing binary like a priority queue, we're using like a complete binary tree here, which just means that we're like filling up all the elements from the left to the right in the tree here. So let's say here we have like A, B, D, E, and we deleted like these two elements here. If we were like going to insert a new item, we had to like insert it here and then the next element here. And then when we need to like insert one more element, because now we have like a perfect binary tree, then we need to insert the next element over here. So we have like a binary tree in order, and we're filling in from left to right, so we can like store it in a vector or array. So we're also going to use this like complete binary tree, as we just talked about, like elements that are just added from the left to the right at the lowest level. So we'll just fill in here at the bottom. So the next element that will be inserted in this tree here will be inserted here, and then the next element here, and then we're just fill in from left to right. And if we're going to like implement that in code, we can use vectors or arrays where we just like store the elements at the indexes. So the root node will be index 1 here, and then we just fill in from left to right here in our array. So it's a pretty nice and also like simple way to implement and store our binary tree in another data structure in C++, and also like other languages. But just like it's good when we're working with complete binary trees, when we're implementing our priority queues in this way. So right now I have some different kind of examples of like how we're inserting and deleting elements from a min priority queue, where we have like the min element at the root node here, and I'm also having an example where we're implementing the priority queue as a max heap, where we have the max element up here, and then we're doing some operations with that. I'm going over some different kind of examples here, and then I'll show you in the code how we can implement it in C++, and how we can like play around with the functions and implement our priority queue, a max priority queue in C++, and see how the like the binary trees are. So first, in this example here, we have like we want to insert 14 in the min priority queue. So here we need to insert our element down here, but we first need to like heapify or arrange our binary tree here, because we have the min element up here, and then we have like large element here down to the left, and then like we also like want like our elements when we're going lower in our tree like to be a lower value, because we're implementing this as a priority queue, where we have like the least priority element up here at the top. So in this case here, if we want to like insert 14, we have to move it up here to position 21. So first of all, we're just moving like 31 down here, and then we're moving like 21 down here, as we can see in this slide here. So we have now moved like 21 down here, and 31, which was here, we moved it down here. And then this node here is free, where we can like insert our element 14, and then we have like sorted or like heapified and arranged our priority queue and like our binary tree again, so it's implemented correct. And when we insert an element, we insert it here from the left to the right, so we have a complete binary tree. So if we want to delete the minimum element in the priority queue, we just delete the root node here, which is in this case 13. And then we need to like heapify our elements again, and we delete the last element here in the like the last node here in our queue, which is like from the right to the left here, in case we're deleting elements. And then we just like go over here again, and we heapify and rearrange our our binary tree. So the 14 here will go up to the empty space here, because now 14 will be the min element in the binary tree here. And then we're just rearranged where we have like 19 goes up here and 21 stays here, and we just go forward heapifying our binary tree. And I'm also going to show you like how we can implement this in code, and how we just like heapify and rearrange our priority queue or binary tree every time we like do some operations on it. So in this case here, we just like move the elements around here, and we insert like the node, like the element here that we deleted the node for, we just insert down here at the bottom, because we have like the highest priorities down here at the bottom. And then again we have heapified our binary tree, so we have the least element or like the min element here at the top of the root node again. And over here to the right we have our complete binary tree, which is now like ordered in the right way, and we have our min element up here again. So another approach to like a priority queue is to implement it as a max priority queue, where we have the maximum element up here at the top. And in this case here we want to insert the number 7. So we inserted like down here to the right here, because we fill in from left to right. And then we see that 7 is a higher priority than 5 in this case here. So we need to swap those elements, and then we swap those elements here. And we can see that we have now like swapped 7 up here, and then 5 will be down here. So now we have like ordered our max priority queue again, and we still have like the largest or the max element here at the top root, like at the root node here, and then the 7 will be here and 5 here. So like the priorities are in order again. And if we want to like delete an element from our max priority queue, in this case here we're deleting the third element, which is this element here with the 3 in priority. So in this case here we need to delete the last node here, because we're deleting from right to left. In this case here at the delete node here, so we will delete. First of all we'll just like swap these 2 elements here. It should have been like a 5 here, but then we swap these 2 elements here again. And then when we have swapped the elements with the last element here, we can then just cut off the last element here that we want to delete from the max priority queue. And when we have deleted our element down here again, we can see that when we heapify our max priority queue or our binary tree, we can see that we now have the new max priority queue here again with the highest element up here at the root node, and then the lower priorities down here in the lower nodes here in the binary tree. So we're now jumping into Sublime Text here, and I'm going to show you like how to implement a priority queue in C++ with the max heap. First of all, you're just going to include the libraries that we're going to use. And then first of all, we have our swap function here, which can swap two elements. So we just pass in here 2 integers, which is the elements that we want to swap. And then first of all, we store one of the elements in a temporary variable, and set that element equal to the other element, and then the other element we set that equal to the temporary variable. So we have swapped the 2 elements around that we have passed to the swap function here. And then we also talked about like this heapify function, which is when we have an unordered binary tree, we need to like heapify it. So we just ordered, and when we're talking about like the max heap here, we also like want the maximum element at the top, and then like the parent is also like a larger element than its child. So first of all, here in the first lines of code here, we find like the largest element among the root, left child, and right tree child, because we could, for example, have when we have insert an element, we could have like 3 as the parent node, and then 1 and 9 as the left and right child node, and then like 9 is the right child node, which will be like the largest element. So we need to swap that with its parent. So here in the lines of code here, we just like find the largest elements among those 3 roots or like a nodes, and then after that like we swap and continue heapify if the root is not the largest. So we just like swap the elements around with the largest element here, and then we just call the function again, because this is like a recursive function that we talked about when we're dealing with this heap, like max heap, min heaps. It's like the priority queue is is a recursive data structure. So again here, if it's not like if the root node is not the largest element yet, then we just like swap the elements here with the largest element with its parent, and then we heapify the tree again. So we just keep doing the same thing until the top element is the largest, which is the I, which passes in as a parameter here to our heapify function again. So we also have this function here to insert an element, as I'll show you some different kind of examples on in the slides. Where the insert function here, it takes the binary tree that we're going to insert an element in, and then it takes an integer, which is the new element that we want to insert. Then first of all, we just check if the size of the tree is equal to 0, because then there's no nodes in it, and we just push back the new number to the tree, so it will now have like one node, which is the root node. Or else we just push back the tree node here, because we have like this complete, like this is why it is so important to have this complete binary tree, because then we can just implement it with a vector, and then we store it from the left to the right, so it just equals to like pushing back the new number to a vector. And that's why it's such a good like cool feature that we're just using complete binary trees, because then it's like easier and more simple to operate with when we're dealing with insertion and deletion. So here, after that, when we have pushed back the new number, we again need to like divide our tree into 2, and then we heapify our tree again with the function up here. So when we have inserted an element and the one of the child nodes are larger than its parent node, and the parent node is like smaller than, like larger than the root node, then we need to like heapify our tree again. So we will get an ordered binary tree again with the max element at the top at root node. We also talk about this delete node function here, which is like it takes the binary tree that we want to delete a node from, and then the element, like the number we want to delete in our binary tree. And then here we just like go through like the whole tree and see if the number is equal to that position in the tree, because again we're dealing with a vector. So it's a really nice implementation of like a priority queue where we're just using vector. And then we just go through a whole vector, like through the whole priority queue here, and check where that number is. And when we find the number, we just break out the for loop here, because then we know where the element we want to delete is at. And then we just swap that element with the last element in the complete binary tree. So we swap those elements, and then we can just cut that element as I showed you in the slides. So when we have our element we want to delete at the last position, in our complete binary tree, then we can just use this pop back function here, which just removes the last element from our vector. And then we just have the for loop here that runs through like the half the size of the binary tree here again, and we heapify our tree as we did in the insertion function as well. So we'll get an ordered binary heap again with our largest element at the top. In case, for example, we delete the largest element, we need to like heapify our tree, so we now have the new largest element at the top. So here we just have a function to print out the array or like the binary tree. So here our main functions, we're going to use some of the functions that we just implemented. So first of all, we know that we need this vector where we can store our heap tree. And then we can insert some different kind of elements here, where we're just going to insert with this function here. We insert like 3, 4, 9, 5, and 2. So this just equals to like pushbacking like those 5 numbers here to our vector. And then if we print out here, I'll just comment this out, and if we print this out here, we can see that our max heap array is now like 9, 5, 4, 3, 2, because we inserted these 5 elements here. So the root node will be 9 in this case here, and the left child node of the root node will be 5, and then the right child node will be 4. And then the 2 child nodes of the fifth, the parent here with 5 as an element will be 3 and 2. So like this is how we implement show a binary heap or a binary binary tree in code, where we just implement it as a vector. So this is just like how we insert elements, and we can also like delete a node. So in this case here, for example, we want to delete the 4th element here, or element 4. So we're deleting the node in the heap tree here with this function that we have implemented, and we print out the array again. So I'll just print it out here again. So we can see that first of all we have our max heap array here where we inserted all the items 9, 5, 4, 3, 2. And then we deleted the fourth item here in the middle, and now we have like 9, 5, 2, and 3. So indeed we have deleted the fourth element here. And when we have deleted our fourth element here, we then again heapified our our priority queue here, so it is in right order, and then our largest element again would be on the top of the binary tree here. So yeah, that's it for this video, guys. We've been over like the implementation of the binary tree, and also like the priority queue with a binary tree in C++, and we have been over some different kind of examples and the methods where we can insert and delete items or elements in our priority queue. There's also like these different two types of priority queue where we can have like the max heap and min heap, where we have the max element at the top root node in the max heap, and in the min heap we have the minimum element like with the minimum priority at the top. So it depends on our application which one of them we will use. But in case like for example we want to like have CPU scheduling, and we also always want to like run the task with the highest priority, we could have used like this max heap here or min heap, and then we will just have popped the last element from then we just pop the root element, because then it will be the max heap, so it will be the max value with the highest priority at the top, and we'll just remove the top element and the root node, and then we'll have the task with the highest priority. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more of it in the future. I'm currently also doing this computer vision tutorial in C++ and artificial intelligence tutorial. So if you're interested in one of those, I'll link to one of them up here, and you can go check that out if you want to, or else I'll just see you in the next video, guys. Bye for now.